Have you ever stopped to wonder, how exactly does Hadoop store files that are hundreds of gigabytes or even terabytes in size without just completely crashing? Well, today, we're diving into the brilliant engineering behind the Hadoop Distributed File System, or HDFS for short, to see exactly how it tackles the unimaginable weight of big data.
Imagine a single file growing so incredibly fast that one single machine just simply runs out of space. It's a real problem. But HDFS solves this using one extraordinarily powerful concept: block storage. Let's unpack exactly how that works.
Here's our roadmap for today's explainer. We'll start with the basic storage principles of HDFS, walk through the actual math of breaking down a massive file, explore why using large blocks is such a game changer, and finally, we'll look at the throughput limitation.
All right, let's jump straight into Section 1, Storage Basics in HDFS, and specifically, the crucial role of memory and distribution.
You see, a massive objective in HDFS is sheer speed. To get that speed, the system actively utilizes memory to temporarily store data in the computing environment. This is brilliant because it allows the system to completely skip the notoriously slow process of repeatedly reading data from scratch. By keeping essential data right there in temporary memory, subsequent processes run so much faster.
So instead of trying to hoard a massive file as one giant, impossible-to-manage chunk, HDFS divides your files into smaller pieces called blocks. It then scatters these blocks across multiple machines, but, and here's the kicker, it relies on the local file systems of those specific machines to actually manage them. HDFS is basically acting as the grand orchestrator, giving us, the users, the seamless illusion of one single massive file system.
Moving right along to Section 2, breaking down a file, where we look at the actual math behind HDFS blocks.
To really grasp this, we have to talk about size. Traditional file systems might use tiny 4-kilobyte blocks, but in HDFS, the standard default size is a massive 128 megabytes. Older versions used 64, but 128 is the modern giant we're going to use for examples today. It's built for big data.
To anchor this concept in reality, let's imagine a single 900 megabyte file that we need to store safely and efficiently on HDFS using that 128 megabyte block size. How exactly does the system handle this massive influx of data? Well, HDFS just does some simple math. First, it divides that total 900 megabytes by our 128 megabyte maximum block size limit. That math gives us exactly 7 full blocks. But 7 times 128 is only 8096 megabytes, right? That leaves us with 4 megabytes left over. So HDFS just isolates that remaining data and pops it into one final, smaller block.
And just like that, our single, giant 900 megabyte file has seamlessly transformed into a total of 8 distinct blocks. We've got 7 primary chunks taking up 896 megabytes and one tiny final chunk holding those last 4 megabytes. These 8 independent blocks can now be securely scattered across different machines on the network. It's such a clean, efficient way to slice up big data.
Which brings us to Section 3, Why use large blocks? Let's look at the 3 major architectural victories of this design.
The first big victory is all about reducing seek time. Seek time is literally just the physical time it takes for a hard disk head to locate the exact position where your data is stored. It's kind of like trying to find a specific book in a giant library. The more you have to wander the aisles and check different shelves, the longer it takes.
So, advantage number 1, large blocks drastically reduce that seek time. When an application wants to read a file, having the data grouped into these massive 128 megabyte chunks means HDFS requires way fewer physical disk seeks. Instead of the disk head darting around 1,000 times to find tiny pieces of data, it jumps once and reads a massive, continuous chunk. It is a huge boost to retrieval speed.
Advantage number 2, it dramatically reduces I/O reads. Because our blocks are so incredibly large, client applications can read a massive chunk of data in one single go. And why does that matter? Because it slashes the number of TCP/IP network connections you need to make. Fewer network connections mean fewer bottlenecks, which creates a beautifully fast flow of data across the entire cluster.
And advantage number 3 is a huge win for metadata management overhead. You see, HDFS acts like a giant directory. It has to store metadata, or data about the data, for every single block it creates. If we used tiny, traditional blocks, our 900 megabyte file would generate thousands of individual blocks, right? That means thousands of metadata entries. But with 128 megabyte blocks, we only generated 8. Fewer blocks strictly equals far less metadata for HDFS to store and manage.
But of course, Section 4, the throughput limitation. Because in the world of computer science, there's always an engineering trade-off.
So here is the crucial catch. A larger block size inevitably results in fewer overall blocks for a file. And having fewer blocks directly means you have fewer parallel tasks capable of reading that data at the exact same time. By consolidating your data into these giant chunks, you are effectively limiting your parallel workforce. Because you have fewer parallel readers working simultaneously, the ultimate limitation is that the overall reading throughput of the entire system gets reduced. Think about it. If your system needs 50 parallel tasks to process data incredibly fast, but your file was only broken into 8 blocks, well, you can only utilize 8 readers. You've brilliantly optimized for seek time and metadata, but you sacrifice some parallel throughput power to get there.
Let's wrap up by returning to a fundamental truth from our source text. These blocks are stored across multiple machines and are managed by the local file systems present in those machines. HDFS creates this stunning illusion of massive unified storage, but it relies entirely on local file systems independently managing these giant chunks of data.
This block architecture is honestly one of the key innovations that made big data processing completely scalable. But knowing this delicate trade-off between metadata optimization and parallel throughput leaves us with a pretty provocative question. If all these blocks are scattered across different local machines, how exactly do they coordinate without losing a single megabyte? Well, that is a fascinating puzzle of distributed systems. Next time, we'll be diving into HDFS architecture and the epic battle between the name node and data node. Thanks for joining me on this explainer, and keep learning.